how are you doing, guys? I'm Rohan, and here's a simple part 2, which is about exploring ImageWoof dataset and debugging without the data block. So these are outlines for today's video. First of all, we are going to explore ImageWoof dataset, working with the lowest level API. Then we are going to discuss the architecture and the new implementations. Then we are going through Mish activation function, self-attention, MaxBlurPool. And then we are going to build our model, what is Ranger, and the difference between fit1 cycle and fit-flat cosine. And then we are going to train our model, and then we are going through what is DataBlock.summary, what if we are using datasets instead of data blocks. So let's get started. Okay, so let's get started by installing fastai by using this line of code here. And for the dataset that we are going to use, we are going to use an ImageWoof dataset. So if we open this link, as you can see, we have this ImageNuttay. So ImageNuttay is a dataset, the subset from ImageNet with 10 different classes. So our goal for today's video is using no pre-trained weights to see how well of accuracy we can get in X epochs. And here we import all from our vision library from fastai. And now let's grab our data. So here we are going to use enter_data method and pass it our URL of ImageWoof and store the path to a path variable. And as I told you, we have a few more datasets available. The first one is ImageNuttay that we saw. It's slightly easier than ImageWoof. It consists of 10 different classes. And the second one is ImageWoof that we are going to use today. It has 10 different dog breeds. And the last one is called ImageWang, and this dataset is used for unsupervised learning. And for today's task, we will use a low-level API, which is a dataset. So here we define our the transformations to be applied to the input data during the training. So the PIL image that create, as we saw in the previous videos, creates a PIL image object from our input data. And our parent label here extracts the label from the parent directory and convert the label to a numerical category. And here we define the transformations to be applied to each individual item. So we will convert it to a tensor, and we will resize our image to be 128 by 128. And here we define the transformations to be applied to a batch of input data. So we are going to flip them, random resize them with 128 by 128 pixels with a minimum scale of 0.35. Then we are going to convert our tensors to a float, and we will apply some sort of normalization. And now let's make our split. So first of all, we need our image files. So here we can get them by using getImageFiles, pass it the path of our ImageWoof dataset, and store the result into items variable here. And here we are going to use a grandparent splitter to split our dataset, pass it our items, and store the result into split IDX variable. And now let's build our dataset. So here we call our datasets object, pass it our items, our transforms, and our split IDX, which is our grandparent splitter. And then we are going to build our data loaders. So here we call our data loaders, pass it our item transforms, our batch transforms, and our batch size. So here we use a batch of 64. And for now, let's show a batch. So here's the batch, and as you can see, the labels here are confusing, so let's fix them. So we can do this by using a dictionary as a transform in our Ys. So here we make our dictionary that says what each label was and convert it to its real name. So to do so, we pass in the dunder get item dunder attribute to our transforms. So let's make it. So here is our transforms that we saw, and here we pass it this attribute. So now we are going to define our datasets and our data loaders again. So here we define our datasets, and here is our data loaders. And now let's show a batch. And as you can see, here's our images with its fixed labels. Okay, so for now, let's talk about some new papers. So we have XResNet, which is the architecture that we are going to use. So XResNet based on the bag of tricks for ResNet paper. Then we have a Mish, which is a new activation function that has shown fantastic results. And we have a Ranger, which is a new optimizer function based on two separate papers. The first one is our Adam, and the second one is look ahead optimizer. And also we have a self attention, which is brings the ideas from Jans into image classification. And we have a MaxBlurPool, which has shown better generalization. And the last thing, we have a label smoothing cross entropy, which is a threshold based rather than yes or no. Okay, so all of these ideas live in the library, but the question is where? How do we get access to them? So let's walk through it. So first, XResNet 50, which simply is a XResNet. So here we define our architecture, which is our XResNet 50. And all of what we talked about can be set as a parameters in this architecture. Okay, so let's go with Mish. So as I told you, Mish is an activation function that has been shown to improve the performance of deep neural networks in various tasks, including image classification, object detection, and natural language processing. So if we take a look at its graph, so as you can see, for the positive values of x, the graph is a straight line, similar to ReLU, and for the negative values of x, the graph will increase negatively, and after that it will decrease and approach 0. And here in the code we define our activation class and set it to be a Mish activation function. And as you can see, we go from convolution to batch norm, then to Mish. Okay, so let's define our self-attention. So self-attention doesn't show up inside the layers, it's more in the forward. And anytime you see this SA is being passed, that is our self-attention. Okay, so let's talk about MaxBlurPool. So it's a pooling function that combines max pooling and blurring operations. So it works first by performing max pooling on the input tensor, which reduces the spatial dimensions of the feature map. Then it applies a blurring operations to the pool tensor, which helps to smooth out the noise and enhance the spatial coherence of the features. So for this one, we will need a custom function. So here we define our custom function that takes two arguments. The first one is a model, which is a PyTorch neural network model. The second one is a layer type old, which is the type of layer that should be replaced with the new MaxBlurPool layer. Then this function is going to iterate through all the models, and for each model, it checks if it has any children. If it does, it recursively calls itself on those children to process them as well. Then it checks if the type of the current model is a layer type old. If it is, so the function will create a new MaxBlurPool layer, with a kernel size of 3 and the padding is set to be true. And then the function will replace the old max pooling layer with the new MaxBlurPool layer and returns the modified model. And now let's go ahead and make our extrasnet 50, which is not pre-trained, and we will use Mish as our activation class, as well as we are going to use self-attention. And the last thing that we need to define in our extrasnet 50 is how many classes out we are going to have. So here we make it 10. And then we can use our custom function, which is convert MaxBool to plur that we saw, to convert our extrasnet 50 MaxBool layers to MaxBool plur layers. So here we pass it our net, which is our extrasnet 50 model, along with the type of layers that we need to convert. Now let's test it out. So we are going to use Ranger as our optimization function. And remember that Ranger functions that we talked about is the same thing as a lookahead on our Atom. So what that means is we can wrap lookahead around any sort of optimizer, so that we have done here. And now let's define our optimization function again. Then we are going to build our learner. So here we build our learner, pass it our data loaders, our model, which is our extrasnet 50, our loss function. So we are going to use label smoothing cross entropy, and our matrices. So we are going to use two matrices. The first one is Tokki accuracy, and the second one is accuracy metric. And now let's find our learning rate. So as you can see here, we are going to use a learning rate with 10 to the power -4 or 10 to the power -3. So for now, let's talk about the difference between fit1 cycle and fit flat cosine. So let's start with fit1 cycle. So fit1 cycle involves training a neural network with a learning rate that starts at a low level and then increases linearly to a maximum value and then decreases back to the original low level. While fit flat cosine, on the other hand, is a learning rate schedule that consists of a flat learning rate followed by a cosine annealing schedule. So the learning rate here is kept consistent for a certain number of epochs, and after this, the learning rate is gradually decreased using a cosine annealing schedule. Okay, so now let's go with our code. So FastAI has some utilities that we can use, and one of them include a synthesized learner. And what that means is we don't need to pass it any data or anything, so we can just make a learner basically out of nothing. So here we define our synthesized learner. And now we can call fit1 cycle and run it with one epoch. And here we plot the learning rate scheduler. So here is our momentum and here is our learning rate. And as I told you, we increases our learning rate up to a certain point and then decreasing it back down. Now let's take a look at fit flat cosine. So here we plot our learning scheduler, and as you can see here, we stay at a high learning rate, in this case for 72% of our patches. And then we bring it all the way down, and we find that this had a lot of better results. Now let's train. So here we are going to train it by using fit1 cycle instead of fit flat cosine, but you can try to train it with fit flat cosine by yourself and you will get a better results. So here we train it with a 5 epochs and pass it our learning rate. And as you can see, here's our results. And we get around 65% accuracy. Okay, so let's go with the second notebook. So this notebook shows how to work with the DataBlock.summary, which is a method that's used to display a summary of the DataBlock pipeline that's created using the DataBlock API. So as we saw in the previous videos, the DataBlock API is used to define how to work with a data loaders object from your raw data. So the datablock.summary method helps you to understand the datablock pipeline by displaying a summary of the transformations and adjustments that will be applied to your data before it's loaded into the data loaders object. And again, we are going to install fastai library by using this line of code here. Then we import all from fastai.vision.all. And we will use ImageWoof dataset like we did in the previous notebook. So here we grab it by using enter data method. And here is the dictionary that we defined to transform the labels as we saw in the previous notebook. And here we define our batch transforms and item transforms, but here in batch transforms we set coda to be false. And we're going to use a batch size of 64. And here we define our data block as we saw in the previous notebook. So here we define our blocks, which is image block and category block, and then pass it our get items, our splitter, and so on. And then we store all of these into a pets variable here. And now to run the summary method, we need to send in what our data block expects. In this case, it's a path. So here we call it and pass it the path of our ImageWoof dataset. Okay, so the first thing that it tells me is we didn't run any issues, so now let's walk through it. So as you can see, it first set up the pipelines and found all the image files in that path. And from there we have two different datasets, our training and validation. And then it set up our pipeline. So the first pipeline is a PIL-based.create, which is the same as a PIL image.create as we saw in the previous video. And the second pipeline is a parent label to grab our Ys and then convert it to a category. Okay, and then it builds a sample through all of these transforms. So as you can see, first it's a grab all the JPEG applies.create, and then it goes through our Ys. So it starts with the image and then grab the label and convert it by using the transformations that we defined in the dictionary. So as you can see here, we have a border terrier, then apply the categorize, which is turn it to a 2. And finally, we have a PIL image that hasn't been resized anymore. Then we can see it goes to after item transforms that is going to resize our images and convert it to a tensor. And we didn't have any before batch, but we have a after batch transforms. Then it's going to build our batch. So the summary method that we saw it will only work if we are in the data block. What if we are using the datasets, which is a lower level API instead of the data block? Okay, so let's go through it. Okay, so here again we define our transforms, our item transforms, and our batch transforms. And then we are going to build our datasets. And we will want to grab the first item from our set. So here we grab the first item from our training dataset. And here we print it. So as you can see, we have an image and a tensor category. And we can display after item or after batch transform pipeline, so we can let them by calling them. So here we call our after item, and as you can see, we are going to resize the image, then we are going to convert it to a tensor. And here we call after patch, so we are going to do flip item, random resize crop, convert it from int to a float tensor, and then normalize. And now we can pass in our items through the pipeline like so. X of 0 has our input and x of 1 has our y. So here we iterate through the list of after item callback in the train data loader. Then we get the name of the current callback, and here we apply the current callback f to the input variable x, and then we print the name of the current callback f and the transformed version of the input variable. And as you can see here, we have this resize and two tensors that we saw before. Okay, so that's it for today's video. Hope you enjoyed.